Good morning, students. Today I'm going to introduce a topic called electrical properties of colloids. So colloids are systems in which very small particles dispersed in a dispersion medium, and although they may appear uniform to a naked eye, and the particles have special surface properties. And one of the most important is that the colloidal particles usually carry an electrical charge. And this charge plays an important role in determining the stability, movement, and behavior of colloidal systems. So when colloidal particles are charged, they attract ions of the opposite charge from surrounding medium. And this will create an electric double layer around each particle. And this electrical double layer which strongly influences whether the particle remains dispersed or start to aggregate. Because of this, electrical properties which are directly linked to the stability of the solution, suspension, emulsions, and many biological systems. And this today's topic includes phenomena such as electrophoresis, where charged colloidal particles move in an electric field, then Donan membrane effect, which explains the unequal distribution of ions across a semi-permeable membrane in presence of a charged colloidal particle. And these concepts are very important in not only in physical chemistry but also in pharmaceutics, biology, medicine, etc. So in today's this section, we will understand how charge develops on colloidal particles, how the electrical double layer is formed, and how these electrical properties will affect the behavior and also the stability of colloidal particles. So start by introducing colloids as dispersions in which particle size lies between two solutions and suspensions. And mentioned that one major reason colloids remain stable is their electrical properties or electrical behavior. So this topic mainly includes four things, that is colloidal charge, electrical double layer, electrophoresis, and about Donan membrane effect, Donan membrane equilibrium. So colloidal particles are not electrically neutral in behavior. They usually carry a charge. Either it could be a positive charge or a negative charge. And this charge mainly affects the stability of the colloidal particle, movement of the particles in an electric field, and distribution of ions near the particle surface. And these concepts are very important in our pharmaceutical field because many suspensions, emulsions, or any other systems like colloidal systems, they all include this electrical property. So here an example was given, that is examples of positively charged solutions include ferric oxide, metal hydroxide, then sulfur, arsenic sulfide, etc. While kaolin is listed as the kaolin, sulfur, arsenic sulfide, all these are negatively charged. And if a particle absorbs more positive ions, it becomes positively charged. And if it absorbs more negative ions, it becomes negatively charged. And like charges will repel each other, so particles will remain separated and they do not easily aggregate. And this contributes to the stability of the colloidal particles. Then the next slide that introduces about the electrical double layer using silver iodide solution prepared by chemical reaction, that is silver nitrate plus sodium iodide gives silver iodide and sodium nitrate. So it will explain that when silver iodide is formed in water, the dispersion medium contains several ions such as Ag plus iodide ion, Na plus ion, NO3 minus, and also some H plus and OH minus ions from water. So if the reaction is carried out with excess sodium iodide, then more iodide ions are available. So iodide ion get absorbed on the surface of the silver iodide particles, and the particle surface will become negatively charged. So I will explain step by step. That is, silver iodide particles are formed by means of precipitation. The medium contains many silver ions, and when the ion is in excess, it will tend to be differentially absorbed on the surface of the colloidal particle. And in this case, iodide ion is in excess. So silver iodide absorbs iodide ions. Therefore, the colloidal particle gets negative charge. This slide explains what happens in the surrounding solution after the silver iodide particle becomes negatively charged. So here, the aqueous solution contains more concentration of Na plus and NO3 minus ions and low concentration of I minus, Ag plus, H plus, OH minus ions near the particle. So because this silver iodide particle contain more amount of iodide ion concentration, they will attract more positive ions, especially Na plus ions, which are called the counter ions or Jajan ions. So the particle surface is negative because of absorbed iodide ions, and a negative surface will attract positive ions from the medium, and these opposite ions will gather near the particle surface, and these oppositely charged ions are called the counter ions or Jajan ions. This slide says that the Na plus ion concentration is highest in the immediate layer of the negative surface, and that forms a compact layer called the stern layer. As the distance from the surface increases, the sodium ion concentration decreases through a diffuse layer called Boyd-Chapman layer. And together, these two oppositely charged regions form electrical double layer. And the thickness is usually about 10 to 100 angstrom. The first layer is called the stern layer. That's a fixed or tightly held counter ions closer to the particle surface. And the second layer is called diffuse layer or the Boyd-Chapman layer. And that is a loosely distributed ions that will extending towards the outside. And the entire arrangement, both these two layers are called electrical double layer. And this electrical double layer is why it is important, because it determines the stability of colloidal particle, and it influences zeta potential. Then compression of this double layer can lead to coagulation of the colloidal particles. This image is showing the electrical double layer at the surface of silver iodide particles. Using this image, we can explain that the center ion is the iodide ion. That is, the silver iodide particle surface with absorbed iodide ions. And around this iodide ion, there lies Na plus ions. That is the compact layer. And beyond that, there is the diffuse layer or the Boyd-Chapman layer. And the image also labels stir plane, particle surface, then Boyd-Chapman layer. And the point to the center that says that center is the negatively charged particle, that is the I minus ion. And the intermediate layer, that is the tightly bound counter ions, that is called the stern layer, that is Na plus ion. And the diffuse layer is called the loosely distributed ions, the ions that are more loosely distributed. That layer is called the diffuse layer or Boyd-Chapman layer. Then next slide introduces about electrophoresis. So electrophoresis states that when an field is applied to a colloidal dispersion, particles carrying charge will move towards the electrode of opposite charge. And this phenomenon is called electrophoresis. And it also says that the particle velocity depends on the strength of electric field, dielectric constant of the medium, viscosity of the medium, and zeta potential. So a negatively charged colloidal particle will move towards the anode. A positively charged colloidal particle will move towards cathode. The faster movement occurs when the electric field is stronger and when the zeta potential is high. So slower movement occurs when the viscosity of the colloidal dispersion is high. So we can remember in a simple way that if more charge is there, more movement, more viscosity is there, means less movement. So more charge means more movement, more viscosity means less movement. Next, explain about electrophoretic mobility. So this slide says that electrophoretic mobility meaning the velocity of particles in an electric field that can be studied using an electrophoretic cell. That means fitted with two electrodes. Colloidal dispersion is placed in a cell. Electric potential or electric current is applied. The particle will move towards oppositely charged electrodes, and the movement is observed through an ultra microscope. So we'll explain step by step. First, take colloidal solution in an electrophoretic cell. Insert two electrodes, positive and negative electrode, and apply electric potential. Charged colloidal particle will start moving, and observe the movement and measure the direction and the rate of movement. So the rate of movement of the individual colloidal particles that depends on charge on the particles, and that is directly proportional to zeta potential. So zeta potential means it is the potential difference between the dispersion medium and the stationary layer of the fluid attached to the particle. In simple words, we can explain zeta potential, that is how strongly a particle behaves as charged in dispersion. And higher the zeta potential means better repulsion between the particle and greater the colloidal stability. So if the zeta potential is high, means the stability of the colloidal suspension is great. So an important point is to remember is high zeta potential means particles will repel each other strongly and the colloidal dispersion will become more stable. And low zeta potential means repulsion decreases and particles may aggregate or coagulate in the dispersion medium. Next is about Donan membrane effect. So it states that when charged macromolecules or colloids are present on one side of the semi-permeable membrane, they affect the diffusion of small ions, including the drug ions, across the membrane. And the slide says that this Donan membrane effect will happen due to an electrical gradient across the membrane, and as a result, the ions with the same charge as the colloid, same charge as that of the colloid particle, they will move to the opposite side and producing an uneven ion distribution, and that is termed as Donan membrane equilibrium or Donan effect. That means due to an electrical gradient, electrical difference across the membrane, semi-permeable membrane, and the ions with the same charges of the colloid, they will move towards the opposite side of the membrane and producing an unequal ion distribution throughout the membrane. And this effect is called Donan membrane equilibrium or Donan effect. So a semi-permeable membrane that allows smaller ions to pass, but does not allow large charged particles, charged colloidal particles, to pass through the semi-permeable membrane. And because colloidal particle cannot pass or cross through the semi-permeable membrane, the ions will redistribute unevenly across the membrane. And this unequal distribution of the particle will create an electrical imbalance and concentration imbalance. And this Donan membrane concept, equilibrium concept, that is important in case of biological membranes, protein-containing solutions, dialysis, and even the drug distribution. In all these cases, this Donan membrane equilibrium effect is important. There is an example for the Donan membrane effect. That is, sodium chloride solution is placed on one side of the semi-permeable membrane, and a negatively charged colloidal solution with its counter ions, that is written as R minus Na plus, on the other side. And the volume of the both solutions on both sides is the same. So large negatively charged colloidal ion R minus that cannot pass through the membrane, but the smaller ions like Na plus, Cl minus, they can move across the membrane, move through the membrane. Because R minus is trapped on the one side of the membrane, ions will distribute themselves unequally or unevenly to maintain both electron neutrality and the equilibrium condition. So we can consider a semi-permeable membrane. On one side, NaCl solution, the negatively charged colloidal particle Na plus, and membrane allows Na plus and the Cl minus ion to pass through the semi-permeable membrane, but the R minus cannot pass. And therefore, an uneven distribution, ion distribution will occur. This results in the Donan membrane effect. This is a derivation of electroneutral state and the Donan membrane, Donan equilibrium equations. It shows that on one side, that is A, mentioned as A, positive charge equals negative charge. So Na plus A is equal to Cl minus A. And on side B, positive charge equals the sum of negative charges. So Na plus B is equal to R minus B plus Cl minus B. These are equation 1 and equation 2. It then states that the equilibrium condition for diffusible ions across the semi-permeable membrane as Na plus A into Cl minus B is equal to Na plus B into Cl minus B. And substituting the previous relation gives the next derived expression. So each side must remain electrically neutral. Side A has only Na plus and Cl minus, so their concentrations are equal. Side B has R minus, negative charged colloid. So Na plus must balance both R minus and Cl minus. And for diffusible ions, the product relation forms an equilibrium. And substitution is the mathematical form of the derived equilibrium. And this equation gives the derivation of the Donan effect. And this equation shows that chloride ion concentration is not equal on both sides because the impermeable colloidal ion R minus alters the ion distribution. And the conclusion is that the presence of non-diffusible charged colloidal particle that produces an unequal distribution of the diffusible ions across the membrane, which is the equation for Donan membrane effect. So, colloids influence. So, as in a brief, you can say that colloids influence the ion movement even without crossing the membrane. And this changes the ionic balance, osmotic behavior, and drug ion distribution. Therefore, the Donan effect has importance in case of biological and pharmaceutical systems. As a summary, we can say that the colloidal particles usually carry either positive or negative charge. The surface charge will attract aggressively charged ions and they forms an electrical double layer. And this double layer has two layers, Stern layer and a diffuse Boyd-Chapman layer. So in an electric field, colloidal particles move towards the aggressively charged electrons, and this is called electrophoresis. Then the electrophoretic mobility that is related to zeta potential. The next Donan membrane effect will explain unequal ion distribution across a semipermeable membrane in presence of non-diffusible charged colloids.